Welcome and thank you for joining the Stories Project lecture on a topic that sits at the heart of sustainable energy transitions, advancing battery innovation through life cycle sustainability assessments, LCSA. My name is Viera Pechancová and I am Senior Researcher and Project Coordinator at the Tomáš Bati University in Zlín in the Czech Republic. In this session, we will explore how life cycle sustainability assessment supports innovation in the battery value chain, guiding the development of cleaner, more efficient, and socially responsible technologies. Over the past 260 years, humanity has experienced remarkable socio-economic growth. The global population grew nearly tenfold, driven by advancements in agriculture, medicine, and technology. Urbanization grew too, with cities becoming the epicenters of economic activity, while global GDP has risen. This economic expansion was fueled by rising energy use, industrialization, and technological innovations, such as the widespread adoption of motor vehicles and mobile phones. However, this progress came at environmental cost. Global greenhouse gases, including carbon dioxide and methane, rose sharply, driving global warming and ocean acidifications, for example. Deforestation and the expansion of agriculture contributed to biodiversity loss, while pollution and nitrogen runoff stressed marine and coastal ecosystems. The interconnectedness of these trends underscores how human development has deeply impacted the Earth systems. To address these challenges, life cycle sustainability assessment offers a critical framework. By evaluating environmental, economic, and social impacts across the life cycle of products and systems, LCSA helps identify sustainable pathways for development. For example, understanding the trade-offs between economic growth and ecosystem degradation can guide policies that prioritize renewable energy, sustainable agriculture, and circular economy principles. Life cycle sustainability assessment is a comprehensive framework that integrates three key approaches to evaluate sustainability of products and systems throughout their entire life cycle. These components include life cycle assessment, which focuses on environmental impacts, such as greenhouse gas emissions, resource use, or waste generation. Life cycle costing, LCC, which examines the economic costs associated with products' life cycle. And social life cycle assessment, SLCA, which evaluates social and societal impacts, including labor conditions, community well-being, and ethical concerns. A critical aspect of LSCA is ensuring that all three assessments operate with the same functional unit and system boundaries, enabling consistent and comparable results. However, this doesn't mean simply summing up the results. Each dimension provides unique insights that must be interpreted individually while contributing to a holistic sustainability perspective. The battery supply chain comprises multiple stages. It starts with raw material extraction, often through mining, followed by the production of battery components, modules, and packs, which could include battery management system. These are then transported, used, and eventually reach their end-of-life stage, where recycling and reuse play a crucial role in recovering materials and minimizing waste. Each of these steps brings specific environmental, economic, and social challenges that LSCA helps address holistically. From extraction to recycling, this life cycle approach highlights the potential of the circular economy in battery systems. Sustainable design, efficient recycling, and ethical sourcing can reduce environmental impacts too, manage costs, and ensure socially responsible practices. Batteries are considered key components in mobile and stationary energy storage systems. Although there are relevant energy and environmental benefits in the battery operation phase, the exploitation of critical raw materials such as cobalt, lithium, manganese, nickel, and graphite needed to produce batteries involves not negligible impacts. Lifecycle sustainability assessment enables the evaluation of all previously mentioned dimensions as well as lifecycle phases, and to provide decision aid in the face of contradicting goals. For example, cost versus socially responsible material extraction. Such an lifecycle sustainability assessment approach requires a multi-criteria analysis and evaluation to consolidate different category dimensions for one evaluation scale. At the heart of the lifecycle sustainability assessment is the standardized methodology established by ISO 1440 and ISO 1444, which ensures consistency and rigor. LCA addresses environmental aspects and potential impacts throughout a product's entire life cycle. A key focus is the global warming potential, an impact category integrated into most studies. Global warming potential is heavily influenced by the battery production side, with processes like coating, drying, and formation. Additionally, the cathode material and electricity required for material transformation and assembly are identified as significant contributors to global warming potential. This iterative, transparent, and science-based approach allows for continuous refinement to minimize impacts and drive sustainable innovation. The analysis performed by International Energy Agency highlights the life cycle emissions of two key battery chemistries: nickel manganese cobalt oxide 811 type of battery and lithium iron phosphate LFP battery in 2023 compared with projections until 2035. Carbon emissions from batteries primarily come from mineral refining, cathode and anode active material production, and manufacturing processes. Despite these emissions, the environmental benefits of batteries are significant. Electric vehicles produce half the life cycle CO2 emissions of internal combustion engine vehicles, and this advantage will grow as the grid continues to decarbonize. Battery chemistry plays a crucial role in determining emissions. LFP batteries have about 1/3 lower lifetime emissions per kilowatt hour at the pack level compared to high nickel NMC batteries. For NMC batteries, emissions are primarily driven by critical mineral processing, followed by cathode and anode material production and manufacturing. In contrast, LFP batteries distribute emissions differently, around 35% from mineral processing, 15% from material synthesis, and almost 50% from manufacturing. Additionally, recycling materials offer significant savings in both cases. The findings underscore the importance of battery design, material choices, and advancing recycling efforts in reducing emissions. Batteries play an important role in reducing CO2 emissions globally, both directly and indirectly. In electric vehicles and energy storage applications, batteries are directly responsible for nearly 20% of the CO2 emission reductions needed by 2030. Additionally, they are indirectly linked to another 40% of reductions as they enable the broader integration of renewable energy into power grids. The economic pillar of life cycle sustainability assessment follows the ISO 1444 framework, capturing costs throughout the entire life cycle. Unlike environmental LCA, where impacts are assessed across multiple categories, life cycle costing measures all data in a single unit, currency, making it highly relevant for evaluating cost perspectives across different stakeholders. For batteries, LCC could include capital expenditures (CAPEX), operational expenditures (OPEX), and end-of-life expenditures (EOLEX). Capital expenditures represents the cost of purchasing and installing the system, including design, engineering, and construction. OPEX encompasses ongoing expenses such as energy use, maintenance, repairs, and of course, material cost throughout the battery's lifetime. Finally, end-of-life expenditures cover disposal, recycling, transportation, and environmental remediation at the product's end of life. Life cycle costing is important in evaluation and comparison of different battery chemistries such as lead acid and lithium ion, particularly in stationary energy storage applications. Key factors like performance, lifespan, safety, and disposal or recycling costs significantly impact the total cost of ownership. Additionally, the economic feasibility of batteries is increasingly influenced by the volatility of battery mineral prices. For instance, lithium prices rose as much as 9 times between 2021 and 2022, reflecting the broader instability in the pricing of critical minerals. These fluctuations highlight the importance of selecting cost-effective and resource-resilient technologies. Social life cycle assessment complements the framework by focusing on social impacts across products' life cycle, including indicators like workspace safety, child labor, and human rights. It highlights social hotspots, particularly in supplier countries and raw material extraction for lithium-based batteries, such as poor working conditions or governance issues. By addressing these challenges, LCA promotes socially sustainable battery technologies. Beyond environmental concerns, social factors increasingly influence the acceptance of low-carbon transport systems, such as electric vehicles. User preferences, including charging times, costs, and habits, shape adoption, with public charging expected to take under 30 minutes, for example. Social acceptance of energy infrastructure also relies on ensuring welfare improvements and balancing impacts, such as price stabilization through grid-level battery storage. Social innovation further enhances sustainable energy systems, exemplified by neighborhood batteries, connecting communities to local renewable initiatives and digital platforms transforming energy use. Integrating social dimensions into energy technologies fosters inclusivity, equity, and energy justice. Sustainability in energy systems borrows also from frameworks that emphasize equity, inclusion, and societal values. Energy justice ensures fair distribution, recognition, and participation in research design and deployment. While responsible research and innovation fosters inclusion and responsiveness in innovation processes. Tools like value-sensitive design and safe and sustainable by design ensure new technologies align with intended social and ethical goals. Frameworks such as donut economics expand sustainability assessments beyond GDP to include social and environmental impacts, and social life cycle assessment bridges environmental and societal considerations. Multi-criteria mapping includes open-ended evaluation of risks and values, while participatory methods like transdisciplinarity and participative systems mapping integrate diverse knowledge from experts and communities. Large language models amplify these approaches by synthesizing interdisciplinary knowledge, making complex frameworks accessible. The 3 EU-funded projects, TwinVector, SMILES, and SOLID, focus on advancing sustainable energy technologies with strong integration of life cycle thinking. TwinVector emphasizes the development of next-generation batteries by fostering collaboration and knowledge exchange, ensuring that sustainability is embedded throughout the battery innovation process. SMILES targets the creation of safe, modular, and hybrid energy storage systems, integrating LCA to assess and minimize environmental, social, and economic impacts across their long-duration energy storage. SOLID pioneers sustainable manufacturing methods for novel lithium metal batteries, utilizing digital quality control and lifecycle thinking too. More specifically, the EU-funded SOLID project is developing sustainable manufacturing of next-generation 4B solid-state batteries using innovative roll-to-roll techniques, including dry extrusion, coating for cathodes, and pulsed laser deposition for ultra-thin lithium anodes. These methods minimize critical raw materials like cobalt and lithium, eliminate toxic solvents, and optimize layer thickness to achieve energy densities above 900 watt-hours per liter, enhancing safety, performance, and life cycle while reducing environmental impacts. This project integrates a sustainability framework based on the Global Reporting Initiative standards aligned with UN Sustainable Development Goals 2. A lifecycle thinking approach ensures evaluation of environmental, social, and economic dimensions. Coming to the conclusion, let's summarize the lecture. Batteries are crucial for the energy transition, supporting zero pollution goals and balancing supply and demand in smart energy systems. While batteries offer environmental benefits, their production involves significant impacts from critical raw material extraction, but also in other life cycle phases, leading to new EU regulations on sustainability and supply chain due diligence. LCSA integrates and examines the environmental, social, and economic impacts of batteries across their life cycle, addressing trade-offs like cost versus ethical sourcing to support sustainable battery development. However, battery life cycle sustainability assessment faces significant challenges. Volatile raw material prices and social issues like workplace safety and human rights highlight the need for socially responsible technologies. Refining data collection, increasing transparency, adopting adaptive frameworks can enhance LCSA relevance and reliability. Holistic approaches to environmental, economic and social dimensions can make batteries central to a just and sustainable low-carbon transition. Thank you for your attention.